morning. My name is Dave Seibert. We're from the Coastal Studies Institute in Wanchese, North Carolina.
And I'm Parker, and we are your hosts for the CSI Summer Science on the Screen series.
So we're educators here at the Coastal Studies Institute, and we're going to host a virtual program every Wednesday morning at 10 a.m. until August 5th. These short programs will investigate scientific topics that we would normally cover in our summer camps if we were able to do them in person.
Most will include videos and activities you can do at home, and all of them will be fun. Today we are going to cover something that we all experience when we go to the beach.
We're educators here at the
and
Coastal
that
Studies
is
Institute.
observing
We're going to
waves.
host a virtual program every Wednesday morning at 10 a.m. Sorry. So if you've ever been to the beach before, then you have seen waves for sure. But there may be some things that you don't understand. Like, where do waves come from? How do they form? Are they all the same size? How do we measure waves? How can waves be useful? There's so much more that we need to know.
All of these questions are ones that we will answer today. First, we're going to start with a short explanation, and then we'll head to our wave tank for a demonstration.
So to get us started, we're going to watch a short video of waves breaking at Jeanette's Pier in February. And so this was during a nor'easter. And so while we watch these waves in slow motion, we want to consider some of those things that we just talked about or just asked. Where did it come from? How does it break? How much power is available in that wave? Would you say that that's a soft breaking wave or a pretty strong, powerful, hard breaking wave? Why is it breaking right there as opposed to somewhere else? So Jeanette's Pier is at least 20 feet above the water line. So seeing these waves coming up underneath the pier, you can really get a feel for how big they are. And we're going to talk a little bit later about how they were created and what it would take to make a wave of that size. And if you spend a lot of time in the water, consider if you would like to be in there with waves of that size. All right, so to get started, now that we've seen some waves and hopefully have started thinking about all those things that we've asked, the first question is, what is a wave? And so, simply put, a wave is a disturbance or a change in a medium. So to have a wave, there needs to be a disturbance. And so we're going to do a really quick demonstration that'll show you a disturbance and what a wave would look like. And you guys can try this at home. You probably have seen this before. In a pond or in a lake. So just imagine if you throw a rock into the lake, right? What happens when you do that? There's waves that form. So the rock would be the disturbance or the change, and then the waves would form because of that disturbance. The waves do not carry matter. And so the wave itself energy is going to move, but the water is not actually advancing. The energy is moving through the water, and we'll demonstrate that as well. And then we're going to categorize different waves based on the direction and the movement of the particles. So there's going to be 3 different types of waves that we're going to talk about today, but we're really going to focus on ocean waves and the ones that we spend the most time with. But there are those 3 different types. One is called transverse waves, one's called longitudinal waves, and the last one is orbital waves. So with transverse waves, the medium is going to move at right angles compared to the direction of the wave. And so if you've ever been in a stadium before and you've seen everybody stand up and do the wave and it go all the way around the stadium, that's a transverse wave, right? You're standing up, but the wave is moving sideways. And so this really short video will show you guys a transverse wave in action, right? And so the slinky is moving up and down, but the energy is moving to the side. And so that's what a transverse wave is. Examples of that is light waves, radio waves, and you can see it on a guitar string as well. Longitudinal waves have the energy and the medium moving in the same direction. And so things compress and expand, and that's how the wave is going to move. And so sound waves and seismic waves are examples of longitudinal waves. And so right now you're hearing me speak And so what's happening is vibrations coming out of my throat are pushing against particles, making them compress, and then that's moving across and getting picked up. And so the sound waves is coming from me and it's reaching you, in this case electronically. But so this short video will show you comparing a transverse wave to a longitudinal wave, and you can really see the difference there. All right, and then what we're really going to focus on today are ocean waves. And so ocean waves are a combination of both transverse and longitudinal waves. They have characteristics from both. And so they're going to move up and down as well as left to right, and they move in an orbital pattern. So we can see, we're going to see this when we go visit our wave tank as well, that the waves are going to move circular, and if we were able to put dye or something in the water, you'd be able to actually see that move around. So some of the questions that we had: where do ocean waves come from? So we were looking at the waves at Jeanette's Pier, watching them break. If you go to the beach today, there's waves, you can see how they break. Where did those originate from? What started those? And so if we do this short demonstration very quickly, we're going to take a penny, we're going to drop it in the water. So the penny is going to be the disturbance, and you can see the waves. So the penny is what caused the waves to form. If we create a bigger disturbance, so we have a washer, it creates a bigger wave. And that makes sense. So we know there's different size waves. In just a minute, I'm going to tell you why there can be different size waves. But a bigger disturbance will create a bigger wave. But our waves in the ocean start with some type of displacement, some type of disturbance, and that disturbance is the wind. So the wind blows over the surface of the water. It causes friction. It causes waves to form in the water, and then those waves can bunch together. And when they bunch together, they're going to form larger waves. So it's all about wind. Here on the Outer Banks, we're known for our wind, right? The first in flight. We have a lot of wind, but that doesn't always equate to great waves, especially when you're talking about using them for surfing or boogie boarding. It's kind of how far away the wind is and how strong the wind is when we really want to get those good waves. But why are some waves larger? So it has to do with how hard and how long the wind blows. So if the wind blows very strong for a long period of time, we'll get very large waves. And there's a term I want you to try to remember called fetch. And fetch is the distance that's available for the wind to blow in a single direction. And so when you have a lot of fetch, the wind can blow for a long time in one direction. It can create very large waves. And that's what's happening in the Southern Ocean. There's no land that breaks up the wind blowing around the Southern Ocean, and so those waves just continue to form and get bigger and bigger. All right, so when we go to the wave tank, we're actually going to ask you to look and collect some data. And so I'm going to tell you the characteristics of the waves that we want you to collect. And so try to remember these, but Parker will remind you once we get down there. But there's three basic characteristics that we're going to cover today. The first one is wave height. And wave height can be measured in multiple ways, but think about it. Wave height is the top of the wave to the bottom of the wave. So the crest is the top, the trough is the bottom, and we need to measure the distance in between. And so you can measure wave heights, because you're going to look at more than one wave, by measuring the maximum wave height over a period of time and recording that information, or measuring the average wave height of the highest 3% of the waves. We call that significant wave height, or just measuring a single wave. And so today, we're going to ask you to measure a single wave, but if you think that's too easy, you can get the average wave height, so measure as many waves as you can, and then take an average of the top third. Another parameter we want you to measure is wave period. And wave period is the time in seconds that it takes for an entire wave to pass a single point. So we have the entire wave cycle from crest to crest. We want to know in seconds how long did that take to move past one point. Wave period is a really important parameter to think about when you're using the ocean, because it's not just the height of the waves that matter, but it matters how close they are together. So if you're using the ocean for any type of recreation, if it's a very short period wave, it makes it really uncomfortable in a boat or harder to get out past the break for surfing. And so those longer period waves may have more power when they actually break, but using the ocean is easier because they're further spread out and it's not as choppy. And then the last parameter we want you to measure is wavelength. And wavelength is actually the distance in between crests. So we're measuring all of our distance today in centimeters, and we'll provide the ruler and all the tools that you need. But we're going to measure the distance in centimeters between two crests, and that's going to tell us how long the wave is. So just a couple more quick things. In fact, at this point, we're going to ask Parker to go down to the wave tank room and get ready to host us down there.
Great. See you down there.
But there are kind of two types of waves in the ocean. We have deep and shallow water waves. And so deep water waves are fast-moving waves. They don't feel the bottom, and so they're not slowed down at all by the bottom. They're long, low, and fast. And then when they get closer to shore, they start to feel the bottom. And so then they start to stand up a little bit more, and they slow down. And that's where we might see them bunching together as well. And so at some point, they're going to slow down enough so the bottom of the wave is going to feel the bottom of the ocean, and it's going to start to slow down, which is going to cause the top of the wave to move faster than the bottom of the wave. And that's going to be when they get very steep and then break. And that actually happens at a specific ratio. It's when the height versus the length is 1/7. And so how the seafloor is shaped is really going to impact how those waves break. So a very gradual sloping seashore will have very weak waves, because I like to think about it, if you ever see a toddler run into the ocean at full speed, right? His feet eventually start going slower than the top of him, and he'll topple over. It's the same thing with the waves. When they feel the bottom of the ocean, if it happens very quickly, they'll fall very quickly. If it happens very slowly, they'll gradually break. And so the bathymetry, or the bottom of the ocean, plays a big role in that. And then as that height stands up really tall, we can get the different types of waves that are breaking. And when we consider our coastline, out here on the Outer Banks, we have sandbars, but we don't have any rocky reefs. We don't have any real jetties that you can surf or anything like that. But the shape of the coastline can also impact the waves that we're seeing. And so reflection can take place when waves bounce off of a surface and go back out. Refraction is when the wave is going to bend based on speed. And so if it's shallower in one place and deeper in another, and the bottom of the wave feels it, it may actually bend the wave. And then diffraction is bending waves around an object. So something like a point or a point break could have those waves bend around, and that would be something that could happen called diffraction. All right, so why do we need to know all this? How do people use waves? How do you use waves? Right, we use waves for recreation. Skimmers, surfers, boogie boarders, all people that use waves. People that are very good at chasing waves or trying to get the waves when they're best are kind of amateur meteorologists, and they understand all these different processes and how they all need to come together. And here at the Coastal Studies Institute, we actually study waves. And so we have an oceanographer that puts out these buoys called wave rider buoys. And the buoys attach to the bottom of the ocean with a big bungee cord. And when the wave passes over or underneath the buoy will go up and down, and we can measure that movement using the same technology that you have in your cell phone. So if you turn your cell phone and the screen flips, that's called an accelerometer, and that's the same technology we have in these buoys. And the buoy has an antenna on top that sends it real-time information that you can get on the internet. So we can see what's happening 8 miles off of Oregon Inlet right now today because of this wave rider buoy that's out there. And during Hurricane Sandy, it recorded a wave over 30 feet. So that bungee cord was stretched really far. And at that time, it was one of the largest waves ever recorded on the East Coast. And that leads us to, why do we study waves? Why is CSI so interested in understanding the nearshore environment? And the main reason is because we're interested in using ocean power or ocean waves to create electricity. And so as another form of renewable energy, we want to be able to understand the environment so we can know how to utilize it. And so there's an ocean energy program here at the Coastal Studies Institute that we'll touch on during some of these other science summer programs, that we're really looking at taking ocean waves and ocean currents and making usable electricity from it. So that's our basic explanation about waves. At this point, we're going to head down to the wave tank room, and we're going to ask you to make some of those observations, and Parker's going to walk us through that.
Here we are at our research wave tank in the basement of CSI. We're going to use a big hydraulic paddle to create waves of different sizes. Remember, we learned wave height is the distance from the crest of the wave to the trough, and today we're going to measure that in centimeters. Wave period is the time it takes an entire wave to pass a single point, and we measure that in seconds. Finally, wave length is the distance between two waves, so we can measure the distance between crests in centimeters. We're going to show you the waves, and we want you to record those 3 parameters: wave height, wave period, and wavelength. Let's start with wave height. Okay. Now we're going to measure wavelength. And now we'll measure wave period. That was wave number 1. Now we'll do a second wave. First, we'll do wave height. Okay. Now we're going to measure wavelength. And now we'll measure wave period. That was wave number 2. Now we'll do wave number 3. First, we'll do wave height. Okay. Now we're going to measure wavelength. And now we'll measure wave period. Did everybody get their waves recorded? Let's head back up to Dave in the studio and we'll talk about our results.
Thanks, Parker. Let's talk about that first wave. Hopefully you found that that first wave that we asked you to record the measurements of had a height of 5 centimeters. And so remember, that's just measuring the top to the bottom, just the same way that you would measure your own height. Hopefully you found that the period of that wave was 1 second. So if you looked at the stopwatch and waited for a whole wave to pass, it would take 1 second. And the most difficult one is wavelength. And so when we measure wavelength, we need to see 2 crests on that ruler at the same time. And so that's pretty difficult to do while the wave is moving, but you should have got about 130 centimeters wavelength. If you didn't get those answers, there's some things that you could try to make it better next time, or if you wanted to rewatch this video, you could try to take more measurements and do an average. That would increase your accuracy. And you could also slow things down. So when we're talking about wavelength, if you were to take a picture of the waves passing over top of the ruler, you would have more time to see actually how far apart things were. So wave number 2 was a 10 centimeter wave, so it was a little bit taller. It still had a 1 second period, and it should have had 165 centimeters wavelength, or distance between crests. And then for wave 3, it was a 5 centimeter wave, so less height. And hopefully you noticed it only had a half a second period, so they were much closer together. And it makes sense, if they're closer together time-wise, they'll also be closer together when we're measuring them in centimeters. And so that actually only had a 40 centimeter wavelength, give or take a little bit. And so all of the waves in our wave tank aren't exactly the same, just like the waves in the ocean aren't exactly the same. And so if you got close to those numbers, that's great. They're probably not going to be dead on. But just keep in mind how much of a difference that period made. So if you looked at those waves, the first two were 1 second period, the third wave was a half a second period, and it looked a lot different just visually. So you can imagine being out in a boat in those waves, how different it would feel to have a half a second period versus a 1 second period. And so keep that in mind. And it's not just wave height that we're interested in when we're thinking about the ocean, but also all these other parameters as well.
So now we're going to challenge you to build your own wave at home. You can take a look at the video that we're about to show, and you can make one of these at home for a demonstration that you can control. One of the other things that you can also do is visit our website, and you'll find a short activity where you can look at some of the real-time wave data that is happening right now today. You will be able to see how the data recorded and is different from the forecast, what they thought would happen, versus what was actually occurring at that time.
All right, and so lastly, we thank you all for tuning in, and we have a calendar available online as well as right here. You can take a quick look at it. That's going to tell you about the rest of the summer. So next week, our topic is going to be estuaries and plankton. We're going to have plenty of stuff that you can do at home. And anytime we do something that you can do at home, we'll have a materials list for you online. And there's also usually a video accompanying it that explains what to do. And then July 15th, we plan to do something with fish biology and adaptations. The 22nd, we're going to focus on marine mammals. The 29th, we're going to focus a little bit more on the art side of things and do shapes in nature. And then we're going to finish up by talking about one of my favorite things, which is shipwrecks, on August 5th. So please join us next week. And if you have any questions, we'll monitor the chat for the next couple minutes, and we'll be able to answer that for you. Thanks, and have a good day.
Thanks, guys.